Okay, so we're on page 215, and we're looking at correlation and regression. So correlation is the statistical technique that is used to determine if one variable, such as the number of days hospitalized, changes or is related to another variable, such as incidence of hospital-acquired infection. So when the independent variable, the number of hospital days, causes the dependent variable, infections, to increase, then the direction of the correlation is positive, it increases to the right. When the independent variable causes the dependent variable to decrease, the direction of the correlation is negative and it decreases to the right. Different types of data require different tests for correlation. So we have Spearman's rank order correlation, referred to as RHO, R-H-O. This is used to test correlation with ordinal and ranked data. The primary test used for the continuous data is the Pearson's correlation coefficient, denoted as lowercase r, which is a calculated score that indicates the strength and the direction of the relationship between two variables. So the values would range from -1 to +1 and are described in the figure on the next page. It is not possible to conclude from a correlation analysis that the change in a variable causes the change in another variable. A correlation, whether positive or negative, it actually does not prove a causal relationship. And when we're looking at regression, regression is used to describe the relationship between a dependent variable and one or more independent or explanatory variables, or how much the value of the dependent variable changes when the independent variable changes. So regression is common in observational studies where the researchers need to assess multiple independent variables or need to control for many confounding factors. There are three types of regressions. There's the linear regression. This is used with continuous data. There's logistic regression. This is used with categorical data. And there's the Cox, C-O-X regression for categorical data in a survival analysis. So if we look up, we can see an example with the dots. We have three scenarios. So when they're all over the place and they're non-linear, there is said to be R equals 0 or no correlation. With a negative slope of 1, we have R equals -1, and we have a perfect downhill or negative linear relationship, and that is the negative correlation. And then with the positive correlation, where the R equals 1, we have the perfect uphill positive linear relationship. And then we're going to move into looking at specificity and sensitivity. So with lab and diagnostic tests, these are used to screen for and diagnose medical conditions. Interpreting sensitivity and specificity correctly is required to answer these two questions concerning the validity of lab and diagnostic test results. So first, if the result is positive, what is the likelihood of having the disease? And if the result is negative, what is the likelihood of not having the disease? So let's look at the sensitivity and the true positive first. So sensitivity describes how effectively a test identifies patients that actually have the condition. The higher the sensitivity, the better. A test with 100% sensitivity will be positive in all patients that have the condition. Sensitivity is calculated from the number of patients who test positive. Out of those who actually have the condition, sensitivity is the percentage of true positive results. With specificity, we have the true negative. So specificity describes how effectively a test identifies patients that do not have the condition. So the higher the specificity, the better. A test with 100% specificity will be negative in all patients that do not have the condition. So specificity is calculated from the number who test negative out of those who actually do not have the condition. And this is the specificity as the percentage of true negative results. So we have a grid down below. So we have our test result and the have condition and not have condition. Positive as AB, negative as CD, total is A plus C, B plus D. So with sensitivity, the calculation would be A over A plus C times 100. To get specificity, it would be D over B plus D times 100. A denotes the number that have the condition with a positive test result. B denotes the number that does not have the condition with a positive test result. C denotes the number that have the condition with the negative test result. And D equals the number without the condition with the negative test result. So sensitivity and specificity calculations and interpretations. We have the tables below, and they show how sensitivity and specificity are calculated for two lab tests used in the diagnosis of rheumatoid arthritis, or RA. Cyclic citrulline peptide, or CCP, and rheumatoid factor, RF. So based on study data, we have CCP with a sensitivity of 98% and a specificity of 98% for RA, while RF has a sensitivity of 28% and specificity of 87%. So using the RF lab test as an example, a sensitivity of 20% means that only 28% of patients with the condition will have a positive RF result. And the test is negative in 72% of patients that actually have the disease. And the diagnosis is often missed. So a specificity of 87% means that the test result will be negative in 87% of patients that do not have the disease, but 13% of patients that do not have the disease will test positive, potentially causing an incorrect diagnosis. So let's look down below. So we have our CCP results in the columns on the left, and then the RF results in the columns on the right. So let's first look at, again, we're looking at diagnosing rheumatoid arthritis. So with the CCP data, we have positive and negative. We have the column of have condition and does not have condition. So when we do our calculations here, we have our A, B, C, and D, and then we have our sensitivity plugged in with the data of 98%. We have our specificity plugged in with 98%, and this is the CCP results. With the RF results, we have our A, B, C, D. We have our sensitivity plugged in to the data, getting 28%, and the specificity plugged in with 87%. So how does this apply to our, let's say, elderly female patient who has swollen finger joints and is referred to the rheumatologist? Lab tests reveal a positive CCP and a positive RF. This CCP indicates a very strong likelihood that the patient does have rheumatoid arthritis because it has high sensitivity and specificity at 98%. If the rheumatoid factor is positive and the CCP is negative, then the rheumatologist would consider the possibility of other autoimmune and inflammatory conditions that could be contributing to swollen joints because of the low sensitivity of rheumatoid factor at 28%. So we are on page 217, and when we come back, we're going to look at intention to treat and per protocol analysis, as well as non-inferiority and equivalence trial designs. We're also going to look at the confidence intervals and forest plot